So let's start with our first example for bending. So the capacity of a beam, excuse me, my voice is a little off, but I'll do my best here. We're going to determine the moment capacity of this concrete masonry unit beam. Note that the compressive strength, so instead of F prime C, it's F prime sub M, they're going to be a lot lower in masonry. So this particular one's 2000 psi. We're going to find out if it's okay for flexure. So we're going to do the capacity and then compare to the demand with the load shown plus self weight. We're going to use 2 number 5 bars in this case. It's a solid grouted section with medium weight block and a coarse grout. So those are things you're going to see when you start going into the tables. Now I have provided the reinforced masonry handbook for you on your Canvas, on our Canvas site. And honestly, that's all you need to do this class. But if you're going to go ahead into structures and you want to buy the Masonry 402-602, the code and specification, you can go to ACI and you guys are student members, or you should join as student members for free. And then you can download it at a discounted price. And here, the handbook is based on the 16th edition, and so that's what we'll follow of the code. There's not a ton of changes. If you're going to buy a copy for yourself, like I bought one for myself, and I bought the 2022, which just came out last year, and that's the most up-to-date one, and you certainly would be able to follow along there too as I go. But the Masonry handbook, much like the PCI handbook for pre-stress, has a lot of detail, refers directly to the code, and pulls out the chunks of code you need. So you can go through with this free item and it'll show you where stuff is in the code and it'll show you those equations. So I'm going to follow the handbook here for examples. They usually will refer to where things are in the TMS or the Masonry Society design code, and sometimes I'll give you that number as well if you have the code and want to look it up. But let's start real quick here and do a little deeper dive into the handbook so you can see what we're up to, because this is a good place to follow an example in addition to my examples. So chapter 5 is ASD design in the handbook. 5.2 is flexure. And so if you go through the handbook, what you'll find is the things I did in the notes in the last module actually go through some of the figures are the same, in fact, pulled from here, but it's just a high-level summary of the things we already did. For instance, here's the modular ratio, steel over masonry, the neutral axis location, and talks about KD. If you go in here, they'll derive, talk about the JD lever arm, how to solve for the K factor that we'll use in some of these terms. I'm going through this quick because we already did it. They've got a nice 3D picture of the stress distribution in the masonry, because we've got the grouted section. In this case, it's a 2-course wall, or a 2-thickness wall, 2-width wall. And then they go through the whole allowable moment computation here, and you can see that we come down to an MS value or an MM value controlling, right? So summarizes into basically this for MS and this for MM. I also uploaded a summary sheet, which you may or may not find helpful. I'm not going to go through that, but it's on the Canvas website. It's like a 2-pager that someone else put together and shared with everybody, just nationally from the Masonry group. And so that also has some of the kind of the handy equations on it. Okay, so as I go through here, the allowable moment is lesser of those two, right? It goes through how to do those calculations and where they're derived from. So we've looked at that already. There's a nice thing that shows you the influence of rho. So rho is in one of those equations. Rho is the ratio, the reinforcement ratio. So we also use that in reinforced concrete design. And it'll show you kind of how that changes things as the reinforcement ratio changes. We can do the design by going through all the calculations. There's also quite a few tables that are helpful if you go in on your computer, or if you can pull up a actual PDF Adobe version, I've got this in here so I can take notes on it, so it's in a different software in GoodNotes. If you pull up where you can see the bookmarks and the tabs, tables and diagrams are in chapter 14. Okay, and the first one is allowable stress design tables and diagrams. I'm going to refer to that. And then there's other tables like GN3A about properties that I'm going to refer to. So the kind of in portion of this handbook has a lot of handy tables. So I will typically on the first round do the calculation and then tell you how you could find it directly in a table. So they use a lot of tables in ASD design, particularly for masonry. All right, so let's keep moving here. The next piece that is of interest here is they start to go through examples. All right, so here it's going to show you, here's the formulas we need, example stresses in masonry and steel, which is basically one of the examples with the little different shaped section that we're going to do. And it goes through the calculations for you. This is very handy to look back to. So when you're doing your homework, look at the example I do, but you can also go through these examples and it tells you where to get some of the information from tables and other things. All right, so let's go back to our actual example. Turn off that. Okay, so we've got a masonry beam, and looks kind of funny here, but this is the U-shaped beam that we talked about, right? U-shaped beam, and then the interior of that beam is grouted. We're going to use a solid grout. And so this is what we'll often call a lintel beam, right? So over a doorway or to cap off the top of a wall where I need more flexural capacity. And so we're going to do the calculation of this guy. Let's first put on dimensions. So it's an 8 by 24, so 8 inches is the nominal wide. The actual width is you subtract off 3/8 inch. In other words, it's instead of 8, it's 7 5/8 inch is the actual. Likewise, from the top here, 24 would give us 24 would give us 23 and 5/8, or for your calculator, you're going to want to write it as 23.625. Down here, 7.625 inches. So I just subtracted off minus 3/8 for the grout line, basically, on each side. So a total subtract off of 3/8 inch. Based on how they're called out in nominal dimensions. All right, so let's go ahead and start working through this one. Okay. So it's asked, actually, let's go back for just a second. It asks us for the capacity, and then it also asks if it's okay. So we're going to need both the demand and the capacity. So let's go ahead with the loads and get the demand side of the equation here. So I'm going to need self-weight. Oops. And for self-weight, the easiest thing to do here is go ahead and pull this from a table. So this is so basically I'll write TMS if it's from the code. Otherwise, whatever I write is from the handbook. So this is I'm not going to continue to write handbook over and over, but for this one, it's handbook table GN-3A. And if you've got the PDF version of that, if you go to page 577, so I'm going to go over here. I've already gone to, oops, sorry, I didn't go to that. So I'm going to go to page 577. Okay, which is actually page 376 of the book itself, but if you want to find it quickly in your PDF, all right, so here we are. What is this? This is the, oops, no, did the wrong thing here. It was 618 is actual page 577. My apologies, go to 618. There we go. That looks more familiar. Actually, page 577. Okay. So, however you want to scroll through your PDFs, and you can always buy the hard copy of this. Might make it easier somewhat on you, but if you're going to be doing a lot of this design. But for class, it's fine to use the free copy. So here's my GN table 3A. Average weight of walls, pounds per square foot, equivalent thickness. Weight of grout is assumed to be 140 pounds per cubic foot. Okay, so I've got a hollow concrete block. It's not clay, so a CMU type block. I've got medium weight. That's one of the things we specified. So the block part weighs 115 pounds per cubic feet. It's an 8-inch nominal block, solid grouted wall. So all those things were given in the problem. So the actual one I'm going to use is this here, 78 pounds per cubic foot. Okay, so this is a handy table for just getting those weights. Otherwise, it'd be a little bit of a pain to cut to if you look at trying to calculate the weight of the grout, the weight of the sense rounded. So it's not hard, but it's going to take a little more time to do that calculation. So let's look at continuing on with here. So when I go in, I pick a from the table with solid grout, medium weight masonry. Okay. I'm going to get from that table a 78 pounds per square foot. So I think I said pounds per cubic foot. This is the pounds per square foot is what the answer is. So the 78 is in pounds per square foot. So I need to convert this guy. So it's a 24 inch high or 2 foot tall beam. We know that it's actually 23 5/8 or 23.625 or 23.625. It is totally common practice to just use the 24 inches. So that's conservative. All right. Because that's the weight, self-weight. So given all the things that are going into these masonry blocks, I wouldn't round up for D or something like that. For weight, rounding up just means it's a little bit heavier, and we're only talking 3/8 of an inch heavier on that piece. And technically the grout piece has to get carried in here somewhere too, so this is totally normal to do. So if we do this, we should take 78 pounds per square foot and we'll multiply by 2 feet or 24 inches. And I'm going to get 156 pounds per linear foot. Okay. So if I go back to my problem again, I've got 245 superimposed dead and 800 superimposed live to add on to there in pounds per linear foot to get my whole weight. Right, so the weight or the total load, probably weight's not the best. I like to use W as usual. So then we get our 156 pounds per linear foot. We've got the 245 and we've got the 800. And that gives us 1202 pounds per linear foot. That's my load, uniform load. And like concrete and like everything else, we're going to do a lot of uniform loads, not so many point loads. Most of the live loading pieces are given to you in a uniform load anyway. All right, so moment we know is WL squared over 8. This is assumed to be a simply supported beam. So, which is not, which makes sense if you think of a beam, the free length over the doorway or the frame or the opening is that length. And in our case, L was 12 feet long. So I'm going to go ahead, do that calculation. You know how to do all this stuff that I'm doing right now. 1202 pounds per linear foot, 12 foot squared. and divide by 8. And I'm going to come up with about 21,000 pounds, or 21,636 pound-feet. Or we'll go ahead and put this one in kip feet. Let's make that less of a problem. 21.6 kip feet. All right, so that is our demand moment. We'll underline that in red here. It's our demand moment. Right, now we need to look at capacity. We know that the moment capacity is the minimum of M sub m or N sub s. M sub m, which is equal to 1/2 F sub b, capital F sub b, K, K, not K sub j, K times JD, or JBD squared, sorry. Got to get my mind on masonry here. I have to do on wood for a while. All right, M sub s, that moment in the steel is F sub s, P, J, B, D squared. Okay, so both of those are in the handbook and the pages I just showed you in section 5.2. K, we calculate K as the square root of n times rho, so modular ratio times rho squared plus 2n rho, and that quantity, I don't know what it's doing there, minus n rho, and j is equal to 1 minus k over 3. Okay. So those are how I get to the terms and the two equations I need. FB, so that's our bending stress, just like in our capacity bending stress, just like in wood. In this case, that value is equal to 0.45, and I talked about this when we went through the module last week. This comes from the code, so you could look at TMS 402 in section 8.3.4.2.2, or in the handbook, just put HB table ASD 3. So that's in that chapter 14 of the handbook under ASD tables. Okay. And I'll look at that in just a second. Continue this calculation. It's 45% of F prime M, so 0.45, and ours was a strength of 2000 psi, and that equals 900 psi. Okay, so that's the FB term. And let's just go take a look at that in the handbook here real quick. Go to page 524 if you're following along on your sheet. And it's 483 in the book. And what I'm going to go through in here is I can see all the different pieces of this. Let me find the right thing. All right, so allowable working stresses, so ASD, for reinforced solid and hollow unit masonry, which is us. Here is our specified masonry strength, okay, and we use CMU. This is what we're calculating right now is the F sub B using that equation. And for our masonry strength, it's 900. So that's what I just calculated, right? And you can see there's shear stress values and everything else in this table. So this is where we'll come back for those. It's a little more straightforward than in the wood. And the reason that the wood one is so complicated is that there's so many different species of wood. Okay, here I'm just looking at masonry units and I'm looking at different strengths. All right, so we go back here. That's where we got the 900. Okay, I could either calculate or take from the table. This is a very easy calculation, so no big deal to do versus the table. Let's go ahead. We know we need the modular ratio as well, and that's in, but the stronger item on top, so you get a greater than 1. So ES over EM. So we're using 29,000. We're back to numbers that we don't have to look up because this is steel and masonry rather than species of wood. The masonry one is going to be the 900 times F prime N. You can go look in table, in ASD table here, and let me find modulus of elasticity for ours is going to be, you can use these values here. Okay, so you can use the values for modulus of elasticity for ours, CMU, okay, or, which will give you 1.8, which is 900 times 2 KSI. And here's the modular ratio. So I don't even have to go to do that. I can just go straight to the modular ratio for my strength of CMU. I should get 16.1. All right, so if I go in here and do that calculation, right, so it's not that complicated. Either do the calculation or look at the table. I'm just showing you both at the same time. And that does come out to 16.1. So that's my modular ratio, which I also need for these calculations. Okay, so I can use that table or use this guy. Rho is another item I need in here. Rho is equal to the area of steel, A sub S over B times D. Okay, so the area of steel, these are number 5 bars. You can, the same kind of bar we use in concrete. You go look that up and you get 0.31 inches squared is the area per bar. There's 2 bars. And then I've got a B value of 7.625 times D. Okay, so I need to figure out what D is to go ahead with this calculation. So D is the distance, obviously, from, let's go back to our picture here. D is the distance from the top to the center line of those bars. If there were 4 bars, it would be to the center line of the group of bars, right? So I know what I'm going to need here is, I'm going to redraw this, I think, so it's not so crazy looking. So we need to find D. Let's go ahead and add another page and start working on that. Okay, I think I'm going to go ahead and draw the cross section here to help us out. So I've got this, this, this. I'm trying to find D. Let's not do that. So I've got some wall thickness. Come around here and up. It's a U-shaped beam. These are my rebar. So I'm going to have a D value that goes from here to here. So what do I need to know? I need to know the wall thickness. I need to know how far to the bottom of those things, and then I take plus a half diameter. This one, it's actually in one of the ASTM specs, but what we're going to do is go look at the handbook. Okay, it's also in the TMS 402 or the TMS, plus the TMS 602 because it's a spec. The easiest way to take a look at this is probably in the handbook on page 335, which I believe I wrote down what the actual page is. Or actually, let's do on. Luckily, you guys can fast forward. Back to 376. Okay, here we go. 335 in the handbook. And if we look at page 335 in the handbook, I feel like I might not have written that down for you here. So we're going to go look at page 335 in the handbook. This has all the tolerances in it. Okay, so a lot of information here. Masonry, a couple things we have. I know that I have to have the reinforcing bars with a minimum cover for weather. We'll assume this is outside of 2 inches. I have a clear distance between parallel bars of 1 inch. And this should look a lot like what you already have done in concrete, right? Splice information. What else do I need here? That I need to have a minimum. Here's some of my placement. Place within. They actually give you a lot of flexibility in placement within a tolerance of a 1/2 inch. Okay, and let's go back here. The rules that we have is the shell here. Okay, the shell is, and we talked about this the other day, you can use a shell thickness of 1.25 inches, okay, on the face. And then there is a piece that tells us for coarse grout, maintain a clear distance, okay, of at least a 1/2 inch for coarse grout between the interior of the masonry unit and the bar itself. Oops. So this is telling me that between the bar and the interior face for coarse grout, I need to have a 1/2 inch. And then I also am going to have 1/2 a bar diameter to get to here. And our bars are 0.625, so 1/2 of that. Then I add these guys up. So that's the 1/2 bar diameter. Right. Add these guys up and I get 2.1 inches. If it was interior, it would need to be greater than 1.5. If it was exterior, it'd be greater than 2. Don't remember if we said, but either way, it's fine. Right. So I'm going to use that. I've got 2.1 clearance. So I made all those items. And so D I can take as the 23.625 minus the 2.1 inches, and I get 21.5 inches, 525. But particularly in masonry, when you get a 1/2 inch um, uh, tolerance on the bar, it doesn't matter. So to the nearest 1/10 of an inch is fine here. So now I can go ahead and get the rest of that calculation for rho with my D value put in there, and I get 0.0038. Okay, so that's my reinforcement ratio. There's not in the code any specified AS min. Okay, so no required AS min, and these are really lightly reinforced typically. The rule of thumb for grade 60 steel, so I'll just put a rule of thumb. Is to have rho greater than or equal to 80 over Fy, so that's going to be 80 over 60,000 in our case, and I don't require that you check this. 0.0013. Okay, so rho a little bit bigger is bigger than this. That's no problem. So, doesn't hurt to check that to make sure that you've not messed up your calculations or ended up with a, way too small amount of reinforcement in there. But in this case, that's okay. And I'm going to go on and continue some of my calcs. So I'm going to use n times rho a bunch of times. So let's go ahead and just do that calculation. and we get 0.0618. Sorry, this has ended up being a long video because I did that intro. K is going to be 0.295. J is going to be 0.90. And those formulas were on the first page when we did this. F sub S, talked about this also, for grade 60 steel is 32,000 psi. For grade, that is grade 60 steel. All right. This is in, if you want to find this, you can find that in the TMS at 8.3.3.1 or in the handbook table ASD-1C. Okay. So I'm not going to go scroll to that. You'll see it if you go there. So now let's find our moment. And we know it's equal to the minimum of the two options. One was the 1/2 times 900 times 0.295, 0.9. So just go back and look at those formulas on the first page of this, of these notes, or the beginning of the video. Or 32,000 times 0.0038 times 0.9 times 7.625 times 21.5 squared. So what am I doing to save you going back in the video here? Is these guys, all right? M sub M or M sub S. And we were just going through, after I wrote this down, all we've been doing is going through and figuring out what each of those values are in that equation. Okay. So M is the minimum of, if I do those calculations, I get 421.1 kip inch or 386 kip inch. Probably get rid of the 0.1 there. And the minimum is 386, which is equal to 32.1 kip feet. So we can go back and look at that for flexure. So I get 32.1 is the capacity, which is greater than 21.6, which is the demand. So it's okay for flexure. Okay. Since our controlling case is the M sub S value, right? This is M sub M and M sub S. So the steel controlled, and it's an under reinforced beam, which is what we used to, or what we like to have in concrete, reinforced concrete design, but here we're allowed to have either. This one actually is, these two numbers are pretty close, and it's pretty close to balance. All right, so that wraps up this first example. The actual problem itself would have probably taken less than 10 minutes or even 5 minutes if you had done it before. But I started out with a little overview of the handbook. Go ahead and download that, or feel free to buy a hard copy if you'd like. You can order it from, I think, the Masonry Society. But have that PDF handy when you work on your problems. It's a very helpful between the tables and the example problems. All right, so we'll wrap this